Start streaming. There we go. Okay. And now it looks like we've got some audio and video. Hopefully. Let's not do that. Hello. Hello, hello. Where's the... Let's skip ahead to live broadcast. Well, sorry everybody, we're having a little technical difficulties, but hopefully we're getting things going here. Share. They will go into LinkedIn. Okay, so we're gonna do that, and we're gonna do this. Hey everybody, if anybody's joined, I am just sharing the links across some of my social media for eMasterCam and LinkedIn. So bear with me just a couple of minutes. I know I'm just like showing the same real simple part on the screen, but I'm trying to get everybody the correct link. It's the first time I'm doing this YouTube live thing, so you know, bear with me. I had to install some free software to be able. I didn't know with YouTube Live it's really only set up to broadcast your webcam, and I figured most people probably don't want to see just my face and me talking about Mastercam. They'd rather see the actual software and how to drive some toolpaths and talk about 5-axis trimming. So bear with me just another minute here, and I'll be right with you guys. Let's see, NC programmers. Let's see. All right. So we got that up. I think we put everything else up. So hopefully everybody's got a source to be able to view. And we're actually getting some viewers, which is sweet. So welcome everybody. Let's see. I'm just sending a chat message. I just want to see if everybody can see the chat messages over in the window there. And if you guys can hear my voice okay, because, you know, I'm live, but like I said, this is the first time I'm doing this. So let me make sure. Is there anything for audio? Closed captioning, normal latency. Okay, good. I'm getting a John Ford saying yes. Okay, cool. All right, so we're actually live now, thankfully, and ready to talk about 5-axis trimming in Mastercam. So I was hoping to get one of somebody's been asking me a bunch of questions there. You know, they've been put in a position where they're doing something, you know, that is new to them and they're struggling a little bit. And so I wanted to talk a little bit about 5-axis toolpaths in Mastercam and the basics of that. The easiest thing to talk about is curve 5-axis. So one of the things I've done here, this is an older, really simple part file that I use for setting up a table machine. So, you know, one of the first things we should talk about when it comes to 5-axis, we've really got to take into consideration the type of machine that we're setting up and we're cutting on. I just started uploading a series of videos to my YouTube channel that is an older 5-axis post class that I did in 2017. And the purpose of that post class was to cover how to set up and configure the generic Fanuc 5-axis mill post for a couple different machine types. So specifically, we went through the process of setting up both a gantry 5-axis machine and a table 5-axis machine, otherwise known as a trunnion. So we can, when I set up a 5-axis machine, I do the simplest geometry that I possibly can. And for me, that's a couple of things. I want a drill operation where if I am looking down from the top of the machine, I am drilling in these 4 different axis directions towards the center of my part. So if you imagine coming from the outside and drilling in. In this case, on this particular test, I've got what I like to think of as kind of the foolproof way of setting up and testing a 5-axis machine. Basically, I am cutting at the 4 different quadrants. So I've got some regular contours. These aren't even 5-axis operations per se, but I've got some regular contours, and then I've got a true 5-axis operation, which is a curve 5-axis. So what's the difference between a 3-axis operation and a 5-axis operation? Well, really, there's a couple of things. So in normal 3-axis machining, we're picking what we call a working coordinate system in Mastercam. And the WCS you can think of as, how do I have my part set up on a given machine? So if I go and I pull up the planes manager and I look right now, all of my operations have been created using the top plane and top WCS specifically. So the WCS you can think of is how are the axes on my particular machine arranged, and where is the origin point. Now the origin point can be a couple of things, right? On a 3-axis machine, we're talking about our work coordinate system, our work offset. Most machines these days use G54, G55, G56, and if they have an extended series of work offsets, you're using G54.1, P1 through P48, in some cases P1 through P99 or 100. It depends on the machine configuration as to how many individual work offsets you've got. So the work offset is really an origin point on the machine that you are telling the machine, this is the 000 point of my program. This is the origin of where my NC code is located. And that's an important thing to think about, right? Because we could have, for example, a machine with a really long bed, and we could have 3 of these parts set up side by side. And really, we can machine that with the same program, only calling a new work offset for each location that we're machining at. When we start to get into 5-axis machining, there's kind of this distinction that's made between 3+2 operations and full 5-axis operations. Now the difference between them is that with a 3+2 toolpath, what we're doing is either rotating the tool or rotating the part to a specific angular orientation, and then typically we're locking the rotary axis. We're engaging the brakes on A, B, or A and B, A and C, or B and C. So those are kind of the typical configurations that we've got for rotary naming conventions. Is typically A, B, or C, and you're going to have a pair of them. So with a 3+2 operation, we're rotating the tool or we're rotating the part into position, and then we're just carrying out 3-axis cutting. So typically cutting in X, Y, and Z, and the rotary axes, other than the initial position of either the tool or the part, while we're making that cut, the machine is only moving its linear axes. So it's only moving in X, Y, Z, and we're not moving the rotaries. In Mastercam, all of the tool plane based tool paths start out as a planar cut. And so whether we're machining in an orientation that matches our WCS, so for example, our WCS for this op is top. So if I machine in the top tool and construction plane, we're machining with the rotaries at 0. If I machine with the WCS at top and I change the tool and construction plane to another orientation, so for example, we look back in our ops tree here and I've got a cut here that's top back, so top WCS, back tool and construction plane. I've got one that's at top front, I've got one at top right side and top left side. So what I'm trying to do here is set up, when I first set up the machine and the post and all that stuff, I am looking to make sure that I'm getting the output that I expect. So for setting up a post, setting up 5-axis, what I'll typically do, let me adjust the screen a little bit here. So what I typically want to do is this. I want 4 rotary positions that are going to machine at 0, 90, 180, and 270, right? The 4 quadrant positions of my platter. So, typically with, and I use this example part to set up for a table style machine. But Mastercam really doesn't care. Mastercam is a tool motion based software. We're creating the centerline code of how we're going to move the tool through the material to cut it away. And there's very in at the toolpath stage here, there's really no kinematic information that's available to the toolpath. We have some settings. For example, if I go into my curve 5-axis and we go down and we look at our axis combination, these are some tools that exist in the software for sending the particular axes that are selected for the toolpath to the post processor. But the information really only goes one way. It goes from Mastercam to the post. So even though we're selecting an axis combination, the place where an axis combination kind of does come into play is when we're doing a lathe toolpath, because there that will actually affect the setup of the tool definition itself. For milling, it really doesn't come into play, other than if your post developer has created logic to read the axis combination, well then we could, all bets are off. That you can actually have custom input that is going to change the output in the post. By default, it doesn't. So by default, the post processor, at least the older generic Fanuc 5X mill post, was set up so that you made your configuration changes inside the post processor itself, and you weren't changing output in Mastercam by adjusting the machine definition. Now, CNC Software has developed some new posts that do have that capability, but that's kind of beyond the scope of what we're talking about today. Really, we're trying to get into 5-axis programming and using some toolpaths. So just trying to set the stage a little bit before we jump into toolpath creation, so that you've got a little bit more of the background about differences between 3-axis paths, 3+2 machining, and 5-axis paths. Now, with a tool plane based toolpath, we've got our WCS, and we set a tool plane that is not parallel or matching to our WCS. And inside the post processor uses some vector mathematics and matrix math to resolve the z-axis vector of the tool plane. So if you go through and scour these operations in Mastercam, you're not going to see a rotary angle. There is no rotary angle. All we have is vector information, and we use linear algebra, matrix math, vector mathematics inside the post processor to resolve the difference between the z-axis vector of the WCS and the z-axis vector of the tool plane in terms of a 3+2 toolpath, or we look at the vector information in a 5-axis toolpath, and that format is completely different from the 3-axis format. All right, my wonderful wife just brought me a glass of water here, so gotta give my thanks to her. All right, so if I take this contour 2D right here, and I go select the post-processing dialog, I'm just going to go in and select a post-processor. You know what? I might have to do this in 2020. Hopefully this goes okay with my OBS software. And you guys can still see this. Bear with me one sec, guys. I gotta just make sure I've got some posts set up. Yep, okay, good. Alright. Give me one sec here, everybody. That's it. Okay, hold on one sec. Let me make sure this is saved in the right spot. And let's make sure this is yes, no. Ha. Okay. Sorry about that, everybody. Hopefully. Let's see if we can get a response. You guys see my screen okay for the Mastercam 2020? Okay, getting some yeses. All right. Now let's go. And this is going to be an interesting question, whether or not you can actually see the NC code pop up. Let me add. What's this? It's a window capture. It's a window capture. And code expert. Like that. Oh, look at that. Huh. Alright, sorry guys. I'm new to this it's this OBS software for broadcasting what's happening on my screen, and there's a lot of capabilities in it, but like anything, sometimes it's tough to learn on the fly. Alright, so we were talking about the difference between 3 plus 2, and 5 axis. So I'm going to go back in here. Oh, let's do this too. Hold on. So let me do window 2, disable. All right, so now I think the NC code, there it is. Okay, good. All right, figuring this out, guys. All right. So, okay, in Mastercam, if I take this 2D drill, and I take this contour 2D, and I take this contour here, and I post them out. Oh, let me see if I can. Yes, all right. Post-processing dialog. So there it is. Okay, cool. So if I select post-processor, do this. Instead of outputting the NC file, I'm going to output the NCI file. I'm going to select edit there. Then there we go. And then I'm going to turn that back on. So if we start looking at the NCI file, this is the start of the operation. This is all machine information that comes out. So remember, I just posted a 2D drill, 2D contour, and another 2D contour. We have a bunch of NCI data in 2-line sets, and that each one of these NCI G-code numbers calls a specific post block, either in your post processor or in MPDLL. And basically, all of these preparatory NCI codes set variables. Then we finally come down here to the 1001 code, and this is the first tool change operation. So this is actually the start of file tool change operation, and 1001 calls the start of file PSOF. It outputs your tool change, all that information. Because this is a drill op, we then have a drill cycle. So this is our G81. Here's the canned cycle information, and then we start the next operation. So what you don't see, this is toolpath motion, and there is not a single angle anywhere in this toolpath motion. Okay, the angle for this toolpath gets resolved because we have a 1016 line, 1014, which is the tool plane, and we have a 1027, which is the WCS. And the post processor does the math inside to figure out what angle should be output. The same thing is true if we come down here and look at our contour. So I've got a couple drill ops, then I come down here, there's a bunch of prep, and this right here is our contour motion. So that's the GO, G1, G3, G1, G3, G1 moves, G0. So we start at rapid. So this is tool change. These two lines right here. Then we have a rapid move. Then we have another rapid move right here. Remember, it's a 2-line set. And then we have a feed move. And that's probably our entry line, depending on what kind of lead in and lead out we have turned on. Maybe not, Then here's a lead in arc, G3. Then we have a G1 move, which is a linear move, a linear cut. Then we have a G3 arc out. Then we have a G1 exit move. And one of the things I can tell on here is that we are not using cutter comp for this operation, because you don't see a G41 or G42 anywhere, and no G40 or G140. So this is what a 3-axis operation or a 3+2 operation looks like as far as input to the post processor. So tool plane based toolpaths, 3+2 cutting, are all well and good. But when we start venturing into the world of gantry 5-axis machining, that's where we need to be able to make a contouring type cut like this right here. It can be as complex or as simple as you want to get, but we need to be able to cause rotation on the machine to occur while we're in the middle of a cut. And that's what makes a toolpath a live vector-based 5-axis toolpath rather than a 2D, or we could think of as 2.5D tool plane based toolpath. So a tool plane based toolpath is either 3-axis only, or it's a 4-axis operation, or it's 3+2. So you can have a 5-axis part that is entirely done in 3+2. I do it all the time. There's no live 5-axis cutting that's required. Sometimes you can add it if it saves time, right? I mean, that's really the big thing, is part of the benefit of making any part on a 5-axis machine is the fact that you can accomplish multiple cuts from different angles, using the same or multiple tools to try and perform as many of the operations to cut the part as possible on that 5-axis machine. So we can contrast these 3+2, and really, before I do that, you notice I've got tool plane right side. Oh, and let me go back here. Okay, so we should have, there we go, should have just Mastercam showing. If I go, let's look at these real quick. So let me go pull up our NC code, and let's go look at our NC code, which is, there we go. Is this the whole thing? This is the whole thing. So actually, that's okay. We can still show that. So I posted out the entire program. This first operation, you'll notice, is a 5-axis operation. So we're starting at C90, B90, and we're positioning in XYZ. So we're positioning in XY here. We've rotated C and B. We're coming down in Z and turning on tool length compensation. We start out at Z5, then we go to Z4, then we feed down to Z3, and then we start rotating. And you can see that based on how the geometry is laid out, we're getting a little bit of change in Y, we're getting a little bit of change in Z, but those numbers are staying pretty close to 0 as our C axis is moving, starting at 90 and then winding up. So it winds up, up, and it gets to 450, and then we exit the cut. Now, why isn't it going 0 to 360? Anybody got a guess? Type it in the chat box if you know. Let's see. Somebody's saying machine limits. That's a great guess. Not quite correct. But machine limits, rotary axis limits can certainly come into play. In this case, it's really the way that we've got the toolpath set up. In other words, the starting point and the ending point of the toolpath doesn't match the way we've got that particular post processor set up. So that post is set up to use a different starting point for the rotary 4th axis based on the way we've got the tool plane set. Or so not just the tool plane, but the way that we've got the operation set up. So if I turn on, let me do this. So I'm going to grab this curve 5 axis, and I'm going to turn on the switch here for only display associative geometry. And with this toolpath here, rather than it being 3-axis code, before we look at the actual path itself, we'll get to that, let's look at what the output for the post processor looks like. So I'm going to post out the NCI file, and we'll say NCI overwrite edit, and I'm just going to post out this 5-axis path. But I'm posting out the NCI. So this is the input to the post processor, and we have the same machine information at the top. We have the same type of preparatory information for filling out variable values to the post processor. So each one of these numbers is going to set, and they're all space separated, space delimited. All of this data is going to set the values of variables in our post processor prior to getting to the first tool change. And that's the important part, is we fill out the variables first, then we call the tool change, so we know, what's the first move, what's the next move, what tool are we using, what's the RPM, all that kind of preparatory data. Then we get down into the motion. So this is the tool change, the 1001 code right here with the info. And then what you'll see is G code 11. And G code 11 is VW position. And that combination of XYZ and UVW is typically output as a scaled vector. And we typically output the value of that vector as a 3D length of 1. Now, it doesn't have to be. You can actually control the vector length in the output in the toolpath. So if we go into the curve 5-axis toolpath, there we go. Okay, good. So if we go into the curve 5-axis toolpath, we have a parameter here that lets us change the 3D length of that vector. Now, why would we want to change that 3D vector length? Well, there are a couple of reasons. The post processor is going to take we can think of a vector as a line. So for this discussion, in your mind, just think, all right, we've got a bunch of lines in 3D space. And the way the post processor works for 5-axis output is that we take that line and we use it with vector mathematics and matrix mathematics to resolve two angles in 3D space. Now, in some cases, we may need a higher precision for the rotary axis addresses, and due to rounding errors, we can actually change the length of this 3D vector, and in the post there's mathematics to check the 3D length, and if it's not equal to a length of 1 unit, whether it's 1 millimeter or whether it's 1 inch, that vector gets scaled before the angle gets calculated. But we can actually end up with a way to control feed rates, because there's also some logic that looks at the flute length, min-max on flute length, or min-max to pivot distance on a 5-axis machine in order to do some of this vector resolving. Plus, if you are machining a giant workpiece, sometimes it's just really hard to see a little small 1 millimeter or 1 inch vector. And you'll notice that the default in metric is actually 25 millimeters, I believe. So we can change this 3D vector length if we need to. So after we do our approach move, and this approach move is vertical, right? We're just coming down in Z. Then we start rotating. And so what you'll see is that we've got an X, Y, Z position, and then a UVW position for a line in 3D space. And the endpoints of that line are not both the same in X and Y, because that line is slightly rotated. What does that line look like in Mastercam? Well, let's go back here. And let me make sure I turn that off. So I'm going to take just this 5-axis toolpath. We'll go into backplot. And so in backplot, if I start stepping through it using the S key, you'll notice that we start out vertical, and then we come to our first approach point. Then I use S to step in. That's our first entry move. I'll use S to step in again. Let me turn off quick verify mode. And now, let's make sure we've got our tool vector display turned on. And as I start using the S key, which is step, you can see that the tool is now moving around my curve. Now keep in mind, I had this toolpath created already, right? So we're going to go through and create some toolpaths so that you get to see that process, create some geometry, all that stuff. But I just kind of wanted to show you and talk about the differences between tool plane based toolpaths, 3D toolpaths, that kind of stuff. Now, one of the things that we can actually see, if I start stepping through this toolpath is pretty junky. And how can I validate that? You know, I say it's pretty junky. What would tell you, what would lead you to believe that that statement is true? Let me change something real quick here. Let's go. There we go. That's a little better. So if I go back into backplot, and turn off the endpoint display as well, you can see that my tool's moving around, and at the end of the day, it accomplishes what I wanted it to do, which was enter into at the start of a cut, rotate 360 around, and exit the cut. But the reason I say it's kind of junky is that if you look at the spacing between these vectors, you can see the spacing here versus the spacing over here. It's not even at all. And it's not even because specifically of the way that, number one, the geometry is being driven is in terms of input to the toolpath, and also our tool axis control method. So when we look turn off translucency and fix this as well. Let's fix the display here. Okay. So if we look at some of these tool plane based toolpaths in Backplot, here we've got there we go. I had some random drill toolpath out there in the middle of nowhere. So here you can see that my tool is coming in from the side. It's not coming from the top. It's entering, it's cutting across that line, it's exiting. And then as I step through to the next toolpath, we're just approaching the part from the other side. So cut, cut, cut. And we make our cut there. So this is a 3D 3+2 output because we are changing the tool plane between each toolpath. And it's that change in tool plane which signals to the post processor that we need to output a rotation. If we look back at our NC code output, here I've got my drilling toolpath, and you can see I'm getting a C0 B90. Then I come down here to my next toolpath, and I'm getting a C90 B90. What else am I getting? If you look at the front of that code, that entire path is being output with block delete turned on in front of it. And what that would give you is the ability to skip that output at the machine by just turning on a switch. So if your block delete button was turned on, every line that's got a slash in front of it would get skipped. But why? How did I put those slash marks in front of just those lines, but not the other toolpath lines? Well, that's just a setting in the individual toolpath itself. So this is looks like just after our our first drill toolpath. So there's a first drill toolpath, and then we go down to contour. So let me hide that guy. So if I go down to my contour operation, I'm going to go to my can text function. And what you'll see here is that with this operation, I've got can text block delete turned on. So this block delete, this is a machine stop, so an MO. And then I've got block delete turned on, which turns on the slash characters in front of every line in the operation. Before, with, and after, you notice I've got can text before, I've got can text with, and I've got can text after. That really refers to before, with, and after the tool change. So for example, if I went to after here, and I clicked on block delete off, and I said add after, select OK, and I post process just that operation so we can take a look at it. you'll notice that now I get block delete only in front of the tool change. So if you had a machine, for example, that where you wanted to do multiple toolpaths in a row, but you wanted the ability to restart any one of those particular toolpaths, because maybe you needed to change, cutter radius compensation or make an adjustment of some sort, speeds and feeds, and you wanted to restart at that position, you can tell it to force tool change, but you can use block delete at the before the tool change and then turn it off after, and it will just go from one operation to the next during normal cutting. But if you need to restart, but in order to do that, you have to run with block delete on for that program. So that's kind of the caveat. If I wanted to turn it all the way off, I could do that as well. So I'll just go in here and I'll just remove this. And I'll regen, and then I'll repost it. And so I've removed that block delete output from the operation by turning off the canned text. So we've talked about the difference between a 3-axis toolpath or a 3+2, same thing really, it's a tool plane based toolpath, and a 5-axis toolpath. So let's talk about creating 5-axis toolpaths. I know, for a lot of you, that's really what you came to see here. Before we create the actual toolpaths themselves, I've got this series of kind of 5-axis operations. Let me, that drill is off in the middle of nowhere, so we're going to get rid of that. I'll save this. Now, one of the things that Mastercam has built in order to allow you to do some basic visualizations of these toolpaths. We've got backplot, we've got verify, but the other thing that we've got is machine simulation. Now, the issue with machine simulation really is that it is not tied into your output from your post processor. So unless you pay the money to have somebody develop a post processor for you, where the output from the post is linked to machine simulation, and you have to pay for that option, the machine simulation that you see in Mastercam is really just using the centerline output of your toolpaths, and it has no idea whether your post is configured to match an individual machine. But what I really like about the machine simulation, just the default machine simulation in Mastercam, it gives you a really great quick way to check fit for an operation on a particular machine. So for example, I'm going to take these simple operations that we've created here, and I'm going to go launch machine simulation. So we'll go into simulate. And we'll add capture. Okay. And we should see that pop up in the live stream. There we go. So what we've got here, I loaded it on kind of a default machine simulation machine, whatever is the first one that pops up. And we can obviously change that. But for example, I've got this little block, I've loaded it on this, Haas trunnion, and if I start stepping through it, I'm just holding down the S key on the keyboard, we can start to do things like check clearances, right? We're not necessarily at this point looking at the NC code output, but we can do things like check clearance from the spindle. So, based on my setup and the size of my tool and all that stuff, if I was using a really short tool and this was really close to the table, I could potentially be hitting it, whether it's with my tool holder itself or my my spindle nose or the Z-axis component here. You can check kind of all that stuff from just a quick clearance perspective. I'm going to crank it way down for the speed and see if we can get it to show a little bit of the cutting. There's a delay, there's a lag between the live stream output and what I'm seeing, so I'm just adjusting it to see what you guys can see, basically. So again, we're checking things like clearance. Now, I'm going to exit the machine simulation here. What I'll do is I'll go into the simulator options. Ooh, let me hide that. So I'll go into the simulator options. I don't know if that's part of my output here or not. So I'll have to add that. There we go. Mastercam simulator options. Then you guys should see it pop up. There it is. So we can do a couple of things here. We can set up our stock, whether it's stock setup. In this case, we're using stock setup. We can use fixtures. So if I go and I look, there we go. This guy, this solid, is on level 15. So we're going to make that our fixture. So I'll go back into my machine simulation options. Oh, yep, okay, good. So that's setting our machine first. Let me go back to the toolpath and let me set up our simulator. So we've got a couple of things. In this little option for machine simulation here, we're actually selecting our machine and doing things like choosing some of the simulator post settings and some other things. There are actually quite a few things that are built into the default system where you can set it up to more closely mimic the real machine, your real machine in the real world. Let me check one thing real quick. Everybody. All right. Make sure YouTube here is there. Sorry, I'm just adjusting a couple things in the background, everybody. Okay, so for this option here, we can set up our machine. If we look at the Toolpaths Manager and we look at simulator options here, we are setting up the data that we feed to the machine. So we're setting up our stock and our fixture data. So I'm going to go into simulator options here. Underneath fixtures, you notice I can turn it on and I'll set my fixture, and this is going to set it as an actual fixture component, which means instead of being stock where we want to cut in, at least with the flutes of our tool, it's okay to cut away stock. If any part of the tool, including the flutes, collides with the fixture, we're going to get a warning in the machine simulation. We can also control some settings like is cutter comp in control simulated or not, our tolerances, and then under simulation we have a link to this machine simulation in the ribbon bar. So we have kind of the same settings as that other option from the ribbon bar. In machine simulation, first thing we do is we select the actual machine that's going to be used. It ships with some default machines. This one's more like a Haas VF2 with like a TR160 rotary table. If I use the down arrow key to go to the next machine, you'll notice it says VMC HTAC, and the HT stands for head table. So this is a mixed mode configuration machine where we've got a rotary axis on the head that is an A axis, and we have a rotary axis on the table which is a C axis. That's the AC. So it's telling you the default configuration for whatever machine is in the drop down here, and they have a naming convention which helps you easily sort it out. So TTAB is the Haas configuration here. If I go down to here to VMC HTBC, this is another mixed mode machine. It's got head and table axes. So there's a table here, there's a head here. Each one has a rotary, but it's using B on the knuckle up here, and it's using C for the table. Now, there's a Bostomatic. I'm going to go through the list a little bit. Here's another table machine. This is a 5-axis Herco. You notice it's a table AC. Then we start to get into the routers. So this is a Como 5-axis. It's a vertical head. So this is a C and B router. So both rotary axes are mounted on the head. And this is the style of machine that we're typically talking about when we're talking about 5-axis routing or trimming. So when we're talking about composites work or thermoplastics, or we're talking about trimming like a 3D composite sheet or a plastic sheet that's been formed into some configuration, a lot of times we're using some kind of gantry machine where the part is stationary but the tool moves around the part. So that's the Como. We've got one for a laser. If I keep going, here's this Magnum, which is a table. This is a larger, like a 5-axis head. So really, we're a little bit limited in our default machines for what we've got available for a 5-axis gantry style machine. So our gantry options, full gantry, where it's in the head. This is one of them, even though it's not really a gantry style. This is just a tilting head style. So really, we've got kind of this 5-axis laser with a head C and A, and we've got this one with a C and B. So those are kind of the two that we've got for using. And this is the one I typically use when I'm doing this head style. But let's go back real quick, because we were looking at it briefly before, to this AB machine. So I want to show you something else. When we use the defaults, which is an automatic position, and then we go in and we actually simulate it, it takes the bottom of our fixture plate and it puts it on the machine itself. So if I exit here, and I go select my solid. And we regen it with some new parameters. And then I go back and take the same operations and simulate them. Does everybody see what's happened? Because the thickness of my fixture increased, it changed the position where it's at on the table. But let's say, for example, that you hadn't even designed a fixture yet. I'm going to turn fixtures off. And then I'm going to go back in and click on Simulate. Ah, it looks like it's still doing the offset. So let me... Oh, there we go. Okay. So let me close that. We're still hanging on to the old one, so let me fix that. Oh, and I think part of the problem is I've got that piece turned on. So I'm going to turn off that other geometry. And there we go. That's what I wanted to see. Okay, so I've turned off that geometry. And so by default, Mastergam is going to put the bottom of my stock, or whatever's visible on the screen, aligned to the platter or the rotary, or the 0 point of my machine, basically. So sometimes what we want to do is load our workpiece with some simple toolpaths to check clearances, and we want to use that to inform our fixture design. How do we want, how far do we want our fixture to stick out? So what I've done is put some just simple toolpaths on this part, and you can see when I called up, when I called up machine simulation, it was just sitting right there at the platter. So one of the tools that we have, if I go back into the simulator options and I go back and look at simulation, one of the options we have is translation in X, Y, and Z. So translation in X, Y, and Z allows you to take your part and physically move it from the platter on the machine, so you can test, well, how would this be if I refixtured my part in a different location. And typically what we're going to do is something like mess with the Z value to look at tool clearance. So I'm going to add 6 inches to my translation in X, Y, and Z. And then I'll go back and I'll launch machine simulation again. And let me turn it on. And now what you can see is that I've offset the bottom of the part by 6 inches from that machine table just by adjusting the machine simulation. And so now I can, run through the toolpath operations. Here, for example, it's doing my 5-axis cut. I've got it set to stop at the end of each operation. And one of the things that's happening is it's going from the start of each toolpath to the start of the next toolpath without necessarily retracting and without changing orientation before it makes the move. So we end up having to ignore the fact that we're seeing some collisions that are created based on the fact that we don't actually get to see that all that's happening between these cuts, the only change that's happening on the machine, it's not an XYZ position move, it's a rotation move. But because of the way this is set up by default, all the system sees, all machine simulation sees, is that we go and we make a cut. So this is our rotary fifth axis cut. We cut all the way around this circle. Let me make sure we're set to clean up on operation change. And then we make this cut here. So we make a 3+2 cut. And then you'll notice it changes tools and it changes orientation. It just flips to the other side. Well, that flip in the software is going to come with a tool change. It's going to, the old operation here is going to retract, and then we're going to, it's going to go home. It's going to change tools, and the new toolpath is going to approach the part, and it's going to make its cut. But when that happens, that doesn't really show properly in the machine simulation, because again, it's just a default thing. And there are some switches that we can adjust in machine simulation, but it's never going to take the place of a real simulation software like Camplete or Vericut or NC Simul or iCam or any of the other softwares on the market that do true toolpath verification and 3D simulation. So just be aware of that. Okay, so we can take this same set of operations, right? We just saw this on a table style machine. I'm going to go back into the simulator options. I'm going to go to simulation, and let's go select our router. Now this is another great example of where we want to use position to change the location here. So I'm going to go translation in XYZ, and let's go -20, -20, and let's go 15 in Z. We need to go up in Z because we need clearance for our head as we're cutting this part. So now if I go and run simulation, same part, I haven't changed anything about my part. Let's see where we're... Where's my X? Oh, that's negative Y. So we wanted positive Y. So I'm going to exit out of there. I'm going to go back into my simulation. Oh, and you guys probably couldn't even see that, huh? I don't think I was displaying that thing. So let me fix this. All right. I'm going to turn on fixtures. There we go. Okay, so I'm going to turn on fixtures. Underneath simulation, we're going to go positive Y. And then we're going to go launch simulation. And we're going to turn it on. There we go. Now you guys can see it. So because I used a 15-inch offset in Z, and my fixture is not 15 inches tall, you can see the gap underneath my fixture. But again, we just took something that had originally been configured for a table, and now we've just dropped it on a head machine. But we can still use that to do some investigation of, is this fixture going to work for holding the part on my machine? And now you can see my head is swinging all the way around the part. And this is a gantry table system, so X is actually moving on this particular router. The head is Y, Z, C, and then B, and the table moves in X. So now we're going to run the next operation, and because we've already removed that material with the first one, you notice we don't see any metal removal there. And this is what I was talking about the reposition. So the head just flipped around, and right now the machine simulation has actually output some extra vectors to try and get it to properly approach this cut, since it was on the other side. But those intermediate positions were done by what we call the machine simulation post processor, and they don't actually appear in the NCIG code at all. So you can see kind of what we're doing here, and here's another one where it's outputting these intermediate positions to get our tool to the start of the next cut. The other thing that we have to check out for, though, we have to be careful of, is do we have reference positions turned on? Because reference positions can, if we've adjusted a tool plane or made a change, those can move our output to a completely different spot, our tooltip to a spot we're not expecting if we're not careful. So here, with our last cut, we're doing some cutting. Alright, so we've talked about machine simulation, using that as a tool. Let's go and let's create some actual tool paths. So bear with me a sec. All right. That is a terrible material. That's better. All right. So curve 5 axis. Curve 5 axis is the basic vector-based toolpath that is the simplest to use and control when you first start getting into 5-axis cutting. So a vector-based toolpath is a series of tool positions in 3D space, and the difference between the start of the the endpoint of the last position and the next position you're given, the tool is going to move, the tip of the tool is going to move from point to point, so XYZ to XYZ. But the back end of the tool, the top of your vector, is also going to move in 3D space. And it is the difference between two vector positions that creates a 5-axis toolpath. So I'm in backplot here. And here I've got this simple hemisphere. This is a project curve 5-axis toolpath. And if we look at the motion of this tool, and make sure my vectors are on, they're on. I'm going to increase this, not 20, we want 2. So my tool moves, it changes the orientation, and it drops into position. And then as I step along, you can see that what's happening is the orientation of the tool is changing constantly as I step across this surface. When we talk about a surface, I'm going to go ahead and unshade that surface. And what you can see is that mathematically you have a grid of control lines that are formed across any surface mathematically. Internally in the math behind the parametric and the NURBS curve generation types that Mastercam uses, Mastercam uses the parasolid kernel, modeling kernel, for creating surfaces and solids. There are 2 vector directions on that surface. There's a U direction and a V direction. And this mathematical equation forms the surface that we're viewing, that we're using. If we think about that in terms of machining, at any point along this surface, there exists a surface normal vector which is perfectly perpendicular to that surface. It's what we refer to as a surface normal. So if I go and use Analyze Dynamic, I'm going to click on Home here, and then I'll click on my Analyze Dynamic tool. I'm going to go down and I'm going to click on my surface, and I'll rotate my view a little bit. And what you'll see is this Analyze Dynamic normal arrow. And I can drag this arrow along my surface and get surface information. So it tells me, based on my current tool plane, what my current angle from vertical is. So vertical would be 90, flat would be 0, horizontal, what the radius of curvature of the surface is, and the diameter, and the actual point that lies on the surface. Oh, sorry everybody, let me capture the window. There we go. So now you guys should be able to see this little analyze dynamic dialog box. Sorry about that. I always keep forgetting every dialog that comes up. I have to add that as a source to my stream. Maybe one day I'll figure out how to get it to just automatically add any new window that pops up. But that's going to be for next time. So as I drag this arrow across my surface, you'll notice when I get right near the tip, you see how my angle goes to about 89 degrees, almost 90? If I can find a point exactly on the top there, that should be exactly 90 degrees because it would be aligned to my z-axis vector. If I change my view and I look at this from the top and I slide my arrow all the way down to the edge of my hemisphere, you notice what you see? My angle from vertical has changed to 0 because I'm all the way down on the edge of that surface. And the only thing that's changing is the actual point on the surface, which is the back end of the arrow, and then the direction of the normal vector. So my normal numbers are changing here and my point numbers are changing. And keep in mind, this normal vector, this is a 3D length line where the start point is the back end of this arrow and the end point is the tip of the vector. So it doesn't start from the origin. It doesn't start from XYZ 0, which is why these numbers basically always add up to a 3D length of 1. These are the X, Y, and Z endpoint components of a 1-inch long normal vector that I'm analyzing on the surface. And sometimes, if I get at this position, you'll notice that my point is X 1.7247, Y negative 1.2501, and Z is 3.3857. We're also on a 4-inch radius hemisphere. So this is a compound angle if we look at it in terms of machine output, right? So if I put a vector exactly there on my part and used a surface normal line that was exactly perpendicular to the surface at that point, I would use that normal vector in a machine matrix to resolve my A and C or B and C angle values. So a lot of the times we're going to get some piece of geometry like this. Say somebody wanted you to cut a 4-inch sphere. Well, where would you start? And a lot of times our material is going to come to us in rectangular form, so we're probably going to create a rectangular block here. And we're going to use some kind of 3D toolpath to machine away the excess material. Now there's some new features that have come out in Mastercam, things like automatic 3+2 roughing, which you can kind of manually adjust to do it in specific ways. Or you might just use regular tool plane based toolpaths and set some depth limits to rough this thing out. But when it comes to plastic style parts, we tend to not do a lot of roughing, and this is true also with composite parts. Most of the time you've got some pressed panel and you're going to do some routing to trim it out. So let's say that we had this here and we wanted to trim we had some shape on the hemisphere that we wanted to trim. So this is sitting on top of a vacuum fixture and we got to trim something out. So I'm going to do this. I'm going to do wireframe point dynamic. So I'm going to create a dynamic point that's on this surface. And I'm just creating something pretty rough here. It's just a simple kind of example. So I've got all these points that are now in 3D space that I used with just my dynamic creation tool. Now, most of the time this geometry is going to come to you, right? Some design engineer somewhere has told you what they want you to make in the form of 3D digital data. So bear that in mind. I'm just creating something random on the fly for the purposes of my example. I'm going to go into automatic spline. I'm going to pick the first, the next, and the last point. Oh. Yeah, that's what I thought. I was already in 2D mode, which is not what I want. So I'm going to undo that. So I'll do automatic spline again, but I'm going to make sure I'm in 3D mode. And I'll choose my first point, my next point, and my last point. So that's the secret to automatic spline. If you have a series of points, you choose the first point, the next point, and if you choose the first point again as the last point, it will create a closed 3D spline. And again, this is just a real simple example, right? So here's my start point. You can see the end point of my spline. So by default, this is where I'm going to start and end. If I needed a different start and end point, well, I would have to do a break on the spline at some location, and I would then do a series of operations in Mastercam, create new spline from curves, maybe even use my refit spline command. You know, there's a bunch of different things for working with 3D data. But as I said, a lot of times you're going to get this 3D data already coming to you in some type of form. So at this point, I've got a shape that I can drive, which is my cut pattern, and I've got a surface that I can use as my tool axis control method. And let's do this as well. I'm going to make another example real quick. So I'll make a 5" by 8" box. I'm going to go into solids and do an extrude. And we'll extrude it with some draft on it. Then I'm actually going to do shell operation here. Yeah, that looks good. Let's look at this from the front view. I'm going to use the front plane. Create some random shape there. And I'm going to go into solids, extrude. It has to be planar. That's the only really real deal that we have to make sure we pay attention to. I'm going to grab all the wireframe here, move it to a different level. and turn it off. And because we can't, I mean, we could machine that as a sharp corner by changing our tool axis. So there is that option. You know what? We'll do something like that. We'll make it interesting. Okay, so we've got some shape, some edges that we want to cut that don't necessarily line up with anything that is, you know, aligned to one of our machine axes. So what I'm going to do here is do some geometry creation for how I want to cut this shape out. And what we're given already is kind of the edges of this part. So the first thing that I'll do is I'm going to go into wireframe and I'm going to do create curve on one edge. Oh, and we're in 2D mode. I want to be in 3D mode. So I'm going to create these edge curves here because I know I want them. And I'm also going to create one that's not an edge curve. I'm going to do a line by endpoints. And I'll do a line there. I'm also going to go and find the midpoints. And that's kind of an interesting midpoint orientation. Not really one that I want to use, and I'll show you why in a minute. So let's go on this edge. And let's see, and this is another one where it doesn't really line up well necessarily with these other edges. So I'm using the option right to just create a line directly off the geometry I'm given. Now, normally when I'm doing this, I'm going to go back in here and let's lengthen some of these lines. So I'm going to go into modify length and I'm going to extend the way that these lines stick out a little bit. And this actually isn't necessarily that bad because if we want our tool to be angled here rather than straight, and we can control the tool axis just by changing the attitude of the line, just by changing how the line sits in 3D space. So what are our tools to edit those lines? Well, I can do analyze entity properties, which is the F4 key on the keyboard. So here I just clicked on F4, it's given me the line, and here's my start point in XYZ, here's my end point. And if I modify these numbers, I can change the orientation of the line. That's a little difficult sometimes to do, depending on what you're trying to do, especially if you're trying to control the angle. The other thing that I can do is I can take an individual line and I can rotate it. So I can use my transform or xform rotate command to rotate the line if I need to change the angle. So let's look at what happens if we don't do any of that yet. Let's just use those existing lines that we generated and make a 5-axis toolpath. I'm going to do it just for this cut real quick, and then we'll do one that kind of does the whole thing as well. So my preference generally is not to drive solid lines. I find you have more control if you create your own wireframe. It's different strokes for different folks. Some people love driving off the solid. Personally, I like the wireframe. So I'm going to do another color here, and I'll do curve on one edge. So these curves here that I created off the geometry, and this is going to be typical of any of your kind of 5-axis trimming operations. You're going to create the edge curves that you're going to drive with the tip of your tool. But then you're going to create lines or some other type of tool axis control method, and we'll get to that, but you're going to create some other type of tool axis control method. So toolpaths, and you can definitely go up to the toolpath menu here and do curve 5 axis. My preference, because I'm working over in the ops manager most of the time, is to right click and do mill toolpaths. Of course you guys can't see that, so let me see if I got. Oh, won't let me do that. Okay. Same type of executable. Let's see if we can do that. Does that show you? Okay, you know what? I can't show you the right click menu. That's okay. What we're going to do is just go up and choose curve 5 axis right up here. So I'll do the curve 5 axis. Now it's going to bring up my dialog. So the first thing I'm going to do is either select a tool or create a tool. Let's go into the library. And I'll go to my tool filter, and I'm going to use a sharp corner flat end mill. So I'm going to double click on flat end mill so that it will automatically grab all my flat end mills. And then I'll grab my, let's grab a 3/8 bit. So I'll grab my 3/8 flat. It comes in as tool 287. So let's go ahead and edit that tool. And of course, there we go. Okay. We're just going to make this tool 4. Okay, so I've added tool 4. It's a 3/8 flat end mill. Okay, we're going to give it some cutting parameters. In this case, let's do 200 inches a minute because it's a router, so we want to do nice routing, right? So 200 inches a minute. We're going to call this trim corner cut. Okay, so the curve 5 axis toolpath is super similar to contour, right? You're going to take a chain of geometry in 3D space. And one of the things that's important to understand about all of the 5 axis toolpaths, you can see it over here in the tree. There are 3 parts, 3 main parts to any 5 axis toolpath. There is the cut pattern, which is generally how do you want the tool to move on the material you're cutting. In the case of curve 5 axis, it's always a chain. So you've got a chain of wireframe geometry or solid edges that your tool is following. Independent of what you're cutting, so here's cut pattern. So here it's showing you a chain in 3D space. Independent of what you're cutting is tool axis control. Tool axis control is how is my tool oriented as it's moving along the chain. And we have multiple methods. So in terms of the curve 5 axis, we've got these 6 different options for telling Mastercam, this is how I want my tool orientation to be as I'm making the cut. Probably the most common method by far, and the method that I typically use for trimming, is lines, followed closely by surface. So surface means my tool is going to be normal, and that normal vector is based on the definition of the surface itself. So at every physical tool point along that surface, the tool is going to be bidirectionally perpendicular to the surface. So that's what we can think of as a normal vector. The tool is going to stay perpendicular to the surface as we trace our cut pattern. Now, the cut pattern is the path that our tool is following. Independent of the path that we follow, we have what's called collision control. And collision control you can think of as the depth control along the tool axis vector. There's a couple methods. There's on the curve itself, on the projected curve, and there's an option to compensate to surfaces. Keep this in mind. For most 5-axis tool path cutting, you don't want to select a super complex group of surfaces as your cut pattern, because it just doesn't make any sense. You want to keep the cut pattern geometry as simple as possible. And in the case of compensating to something, some kind of organic surfaced shape, you would use what we call collision control to choose surfaces you wanted the tip of your tool to be tangent to, but we are keeping those processes separate. We're divorcing them, right? There's the tip control, which is then can be influenced by your cut pattern, but it's not the same thing as your cut pattern. It's an important distinction to make. So cut pattern, 3D curves. You notice you get 3D curves, you get surface edge for all the surfaces, or you get a single surface edge. Typically we're doing 3D curves or 3D wireframe. So I'm going to go select my curve. My chaining direction is going to establish two things. It's going to establish where my tool starts and stops, and the direction that the tool is going to flow along the surface. Hold on, guys. Let me capture. Wireframe chaining. All right, so I'm in my wireframe chaining mode. Okay, you can see my cursor. It's right now it's set to full chain. So if I click on it, it's going to pause at every branch point. So I'm actually going to go, well, actually it doesn't matter. I'll go just a partial chain, and I'm going to turn weight on. Weight means I have to choose each branch of the chain in succession. Let's start actually on this side. So I'm going to grab that green line as the start of my chain. I'm going to grab this line as the next point, and because I've got weight turned on, it's going to wait for me. So now I'm going to go up that way. So that's the chain that I'm going to cut. That's my cut pattern. And I'll say OK. So that's my 3D curve. Let me... And I gotta turn this back on. There it goes. Okay. So there's my 3D curve. Now, one of the things that's kind of, it's good and bad. Okay, there's, in the toolpath itself, you have the option for a radial offset. By default, in a 2D contour toolpath, the radial offset is always half the diameter of your cutter. It's just built into the toolpath itself. You can use stock to leave, negative or positive, to adjust that offset, but it's always half the diameter of the cutter. Radial offset is independent, so you have to physically set it. Now, there is an option when you pick a cutter, make sure I've got it set right. There is an option when you first pick your cutter, if you select it, and then you go in here and pick your curve, and then you go to tool axis control, and this is different. It's actually going to pop up a little warning dialog box to let you know, hey, this is, this is not half the distance. The other thing we have to keep in mind, this is our direction of travel. Because of that, if I'm on the left side, I'm actually cutting into the part itself. So if I really do want to come on this side, I'm going to be conventional milling. Now, typically that's actually what you want to do for composites because it helps eliminate the tearing, but you got to keep that in mind because it's a manual control. So we can go into the chaining manager and we can flip the side, but we can also flip the direction right here in the curve 5-axis dialog box. Cut tolerance. Cut tolerance is going to look at the shape that we're cutting. So if we're cutting a circle, it's going to determine how many steps we do along the shape. The other thing that comes into play here is maximum step. Right now, the default is 100 thousandths. So every 100 thousandths of an inch, we're going to get a new tool axis control vector output from the tool path itself. I'm going to bump that up. I'm going to bump that up to like a 1/2 inch, 0.5. And we don't have any projection set right now. So projection normal to plane, normal to surface is just set to normal to plane. Under tool axis control, so that's really, if I go back to cut pattern here for just a second, we have to choose what we're going to cut, which is our chain, our compensation type. So if we do want to get 5-axis compensation, like a G40 1.2 or a G40 2.2, we actually have to have a post-processor or something like Complete, which is configured to read this. The default generic 5-axis mill is not. Now, sometimes you can end up using 2D compensation, G41 or G42, if you have a table style machine. But you're really going to have to work with your post-processor vendor or make the edits yourself to get that to happen. Right now I'm just going to leave it set to computer. Under tool axis control, I'm going to choose lines for my method, and then I'm going to go pick them. And we always choose our lines pointing back towards the tool holder. It doesn't matter which order we pick them, as long as they point away from our tool tip. So I'm going to select those 5 lines as my tool axis control lines and select OK. Or was it 5, 6, 7? I can't count today. No, 6. Okay, good. All right. So lead and lag allow us to tilt the tool forward or backwards in the case of lead or lag, or tilt positive or negative towards the side. In this case, we don't really want to do that. I'm just going to leave these defaults as they are. One thing you can control is how far the distance from the curve is as to whether or not the lines are going to get judged as being part of the path or not. I'll just say 0.1 for now. Under collision control, you notice we've got set to on selected curve, which is the correct choice in this case. But we also get a vector depth. So the vector depth is plus or minus along the tool axis how deep we're cutting. So let's go minus 1/4 inch. Let's drop the tip of that tool down. One of the fun things we have, we'll come back to it, is this oscillate function, which actually allows us to vary the tip of the tool, which is super important for composites. If we have enough ability on the bottom, like a spoil board or something like that, or clearance on our fixture, that allows us to make this motion. We'll leave it off for now. Under linking, all the values here are always incremental. The retract doesn't really come into play unless we're doing multiple passes. So really it's just the clearance value right here. You notice we're going to start 4 inches away along the tool axis, so we're going to retract 4 inches from that chain. And I'll say keep the tool down within 300% of the tool diameter. This is all kind of standard stuff. One thing I am going to add under linking, I'm going to click on the plus sign, and we're going to go to entry exit. So the entry and exit options here are a little different. It's not line arc the way a 2D path would be. Okay, it's length, thickness, and height. So length is, and this is always a smooth transition with a series of vectors. So you can think of as length as being tangent or perpendicular, depending on the setting right here. You can change it to perpendicular, and it'll change your pivot angle. In this case, I'll keep it just tangent. And so I'll set a 1-inch entry, and underneath on my exit curve, I'm going to set like a 1/2-inch exit. And we've got a curve tolerance, which is just for the entry and exit here, and it's set to 1,000. That's probably I'm going to drop it down to like 4/10, so we get a couple more vectors. And that's really it. We've given it a cut pattern. We've chosen our tool axis control lines. We've told it we want to cut a 1/4 inch below the bottom of our chain. And we told it how we wanted to approach the part with linking, clearance, and feed plane, and how we want to enter and exit the part with entry and exit curve. So there's a lot more control, but I'm just going to hit OK and let it generate the toolpath. So you can see it is nicely tangent, but it's actually got some drop in Z just based on how, or dropping along the tool axis. So one of the things I'm going to do here is I'm going to go back to my entry and exit. I'm going to add a 1/2 inch of height. So it's actually going to drop in starting about a 1/2 inch above. And you'll notice it's giving me this smooth entry. It's never just a linear thing. So if I go into backplot, and I actually turn on the entire tool path before I go over it with my tool, you'll see that there's my entry motion. I'm dropping down this face, I'm coming up this face, and then I'm dropping up that face there, or going up that face and then exiting. So let me turn off that guy there, and I'll start stepping in. You'll see we do this nice smooth entry. And as my tool is tracing along here, because the angle of my lines is changing, my tool axis is changing. It's rotating. So it starts out, if we look back over here at the top, at the corner here, we're kind of halfway between this vector and this vector here. And then we come to the corner, and we're not really rotating very much here. We're moving along in a linear fashion. So part of what's going to happen, if we look over here, notice how our tool is kind of perpendicular 90 degrees to our cut. Well, by the time we get down here, we're about 45 degrees, which is okay. But then as we're coming this way, we're pushing with the tip of our tool. So we want to start to kind of rotate into being 90 degrees perpendicular a little sooner. So how do we change that part of our cut? We change that part of our cut by editing our tool axis control lines. Now we could certainly copy this guy from point to point, and then copy this guy from point to point, and let it do all the rotation in there. And I may show that in a second. But one of the things I also wanted to show you was constant parameter curve. So we'll do this. I'm going to create a new level. And we'll save that. And on my surfaces ribbon, I'm going to go to surfaces from solid. Now, one of the things that we have on surfaces, we have a positive side and a negative side. So the positive side is known as the normal side of the surface. The back side is known as the back side of the surface normal. If I go up to my View tab, by default, this backside switch is turned off. So when I look at a surface and I rotate it so I can see the back side of that surface, I can't tell any difference between which side is the top and which side is the bottom. So I have to turn on that backside switch. And when I do that, you'll notice that the back side of the surface is kind of shown to us as this olive color. So here you can see the front side of one surface and then the surface that's next to it, this guy right here. Because of our view, we're looking at the back side of it. If I unshade the surfaces, I'm looking at this from the top now, we can see something kind of interesting. If I zoom in on this surface over here, it's a nice flat surface, but look at the UV lines on the surface itself. These lines, column U or column V, in this case let's just call them U, these little horizontal lines run along the direction of the surface that is good for us. These other lines are at some weird angle that is not perpendicular, so the U and the V lines are not perpendicular on this particular surface. That means that depending on which tool we use, we have to be careful about the quality of our surface itself. Sometimes we have to end up rebuilding a surface by either using ruled or net or some different method so that we can create a surface where the UV directions are favorable for machining. In this case, I'm going to go back to shaded mode. I've got my wireframe set to this kind of light green color. And I'm going to go into the wireframe ribbon. And I'm going to choose a create curve command. It's called create curve constant parameter. This is a pretty sweet one because it actually lets you create a curve which lies along the U or V direction of the surface. And I'm sorry guys, I think I can highlight curve slice so that you can see it, but the little help tip isn't popping up, and there's some other stuff that's not popping up just because of the dumb streaming software. I gotta figure out how to get that, how to adjust that. But I'm gonna click on the drop down here and I'm gonna go to curve constant parameter. You'll notice over here, let me just move this over here. Oh, it's not going to let you see it? That's garbage. Okay, sorry. Alright, I'm going to have to do it while it's docked over here. So I'm going to dock it. And you'll notice, if it ever pops back up, there it goes. We have an option, U, V, or both. So I'm going to leave it set to U. And what I'm going to do is come down here, and I'm going to click on the surface. And when I click on the surface, I get this little normal arrow that pops up. And wherever the base of the arrow is, when I click on the surface, that's where it's going to create my normal, or not my normal line, my constant parameter curve line. So I click on it, and you notice you can see the direction it goes. So U is not what I want. I'm going to switch that to V. I like that much better. Now I'm going to do the same thing over on the other side. I'm going to switch between U and V. So I'm going to create these two curves that are close to this corner. Let me also create one in the middle here. And I'll do the same thing over here. But I'll switch it to V. So I've created these new little curves, you know, one kind of in the middle over here, one in the middle over here, and I'm going to go to my modify length. I'm going to go to lengthen, and I'm going to extend the ends of these lines. And we'll turn on our other view over here. We'll save that. What I'm going to do now is I'm going to go into my curve 5-axis toolpath. I'm going to go to my tool axis control lines, and I'm going to go and click on clear. So I'm going to remove those lines, and I'll select new ones. So now I'm going to choose that line, this line, this line, and this line. And then I'll choose this guy and this guy. So what I've got, can't forget that one. So what I've got now is a case where these curves are much more perpendicular to the edge of this surface. These curves are much more perpendicular to the edge of this surface, and my rotation is going to happen here. And I'm doing this all by controlling which specific lines I pick. So now when I go into backplot and I start stepping through this cut, because there's almost no rotation that's happening along that edge, you'll notice what's happening is I'm actually getting my vector output as my maximum step value. So it's actually about 1/2 inch between each one of these vector lines. So now I'll step, and as I approach these vectors down here, what you'll see is that I'm getting my rotation. So I'm getting all my rotation happening, and by the time I get to this spot right here, I'm now aligned with this vector. I don't have this one. I'm not using that line. And let me step along. I've got this line here, and you'll notice because there's some rotation here, I'm getting rotation up there as well. So this is okay. This is nice. But can I clean this up more? Well, sure. So if I look at this back at the beginning, you'll notice one of the things that's happening is I'm entering here, but my tool's kind of pushing. It's not really nice and perpendicular here. And that is because I just used the regular edge curve that was on the part itself. Just because the curve is on the part, you know, it's the intersection of two walls on the part, doesn't mean that it's necessarily a good curve for controlling the toolpath. It means it's easy to create, but it doesn't necessarily lend itself to being a great vector for machining the wall. So what I really like are these two vectors here. They're nice and perpendicular to my edges. So let's clean this up again a little more. So what I'm going to do here, let's get rid of what I'm not using. I don't want that vector anymore, so I'm going to delete it. Now I get a warning that pops up. Of course. So let's go window capture. There we go. And so what I get that pops up is my little warning here, deleting a referenced entity, because one of the lines I selected is already referenced in my toolpath. That's okay. I'm going to say delete all selected entities. My toolpath now goes dirty. Let me hide that window. So now what I'm going to do is I'm going to go back into my geometry that's here. I'm going to take this line. One of the new features here, if I double click, or if I click on my little gnome in here, I can get in. Oh, I don't want to be plain. Hold on. So I'm going to go to transform, dynamic. I'm going to select this line right here. I'm going to hit end selection, and I'm going to go and grab the back end. And right now it's set to move geometry, so I'm going to set it to copy, and we'll copy it from here to here, and then I'll say apply. The other thing that I'm going to do, I'm going to do the same thing. I'm going to do dynamic. I'm going to grab that line, and we're going to set it to copy. So I've copied this line here up to this position, and I'm going to get rid of this line. And I get the warning, and I just said okay. And now under Curve 5-Axis Toolpath, I'm going to go back into my line selection, and I'm going to grab these two lines that I copied and select OK. And I'm going to regen the path. The other thing I'm going to do, because I think it's instructive, is I'm going to go under cut pattern here, and I'm going to bump up my maximum step to 2 inches. And we'll regen. And now, when I look at this in backplot, you'll notice that my tool kind of enters in here smoothly on the cut. Because the vector did not change from here to here, I was able to make a 2-inch long move in my NCI data. If I bump that value up, so watch, if I keep on going, here's another 2-inch move, I hit the corner and I start stepping around because of the influence of these angled lines right here. So let's go make sure, 3D curves, 2-axis control lines. So one of the things I'm going to do here is definitely these two guys I'm going to delete, because I want to make sure I'm using this line. So I'm going to take that line and do a dynamic transform. And over here, I'm going to do this. I'm going to go into my wireframe. I'm going to do a point dynamic. Let me turn off my, oh, you know what? So I did an Alt-E. I did hide to hide my solid because it was getting in the way. I'm going to do point dynamic, and we'll just go off of that point a little bit. I just want a point that's slightly along the curve, not right on the corner here. So now I'm going to go translate this line. We're going to move it instead of copying it, and I'm going to move it to that point. So what I'm doing here is I'm taking this corner, which is how I want my tool oriented for this entire section of the cut, and I'm copying this line to the start or to the end of it here. I've copied it to the middle, and I've copied it right here. And the reason I'm doing that is that in this toolpath, this is all going to be straight. It's all going to be the same orientation angle. All 4 of these are going to be the same angle, and the only rotation is going to be around here where I'm changing from this vector, from these vectors to these vectors. So we'll go look at the tool axis control. There it is. Okay, so I go look at the tool axis control. I select those lines there. Select OK. And then reject. When I backplot, the other thing I'm going to do here just to show you, I'm going to go to the cut pattern and I'm going to bump up the maximum step to 10 inches. And I'm going to reject. And now when I backplot, what you should see is I get some vectors up here where I'm entering. And then so let's do this. Sometimes the toolpath itself can hang on to old vectors, things like that. So I'm going to remove them all. I'm going to save this, and I'm going to run the repair file. And then we'll go back in there. And we'll reselect those lines. I'm going to set my max step to 3 inches for the moment. That's better. So it's still seeing a fair amount of rotation here. So that made this nice 3-inch step there. And it's still seeing some rotation that's happening along there. Now there are some other tricks that we can use to modify that motion and make sure that that the angle isn't changing that much. But because we have to rotate around this corner and it's a flat corner, that's throwing this rotation into our toolpath itself. So there may be a better solution here, and that better solution is just to break this into 2. So I'm going to delete that toolpath, and I'm going to go curve 5-axis. So we'll do a curve 5-axis. We're using our 3/8 flat end mill. $12,000 max. 200 inches a minute. Okay, we're going to go trim first edge. So under the cut pattern, I'm going to do a partial chain. That's my cut pattern. It's that one line. And under my tool axis control, I've got a line here. I'm going to choose that line. And that's it. I don't necessarily have to add everything under the sun. I can keep the control pretty simple. So we're going to go, minus a 1/4 inch on that vector depth. And then we'll set up our linking and our entry and exit. So enter. We'll go 3/4 of an inch, and then exit will go 1/2 inch. And I'll say OK. And the only thing we didn't do is change our side. So under cut pattern, I'm going to go to right. And keep in mind, if I wanted to climb mill, I could simply reverse the chain. And now what you'll see, there's my cut. I'm doing one nice straight cut, but I'm getting a ton of vectors. And what that means is that for this one cut, when I post out my code, let's look at our NC code output. Turn on the window capture. Okay. So now you guys can see the code. And what you'll see is that we've rotated to this angle. C minus 87.943, B 94.558. Now the angle itself is irrelevant because really that is determined by the post processor. And we already know this post really isn't set up quite correctly. Now I've got a whole video series that talks about setting up the generic Fanuc 5X mill post, so I would encourage you guys to subscribe to my channel, check out those post processor videos for the 5-axis, and if you're new to post processor editing, I would start with the basic mill post processor class. That's probably the best place for you to start. See. Okay, so this is all well and good, but we've gotten a rotation position, and then we're just getting a bunch of X, Y, Z output. So all it's doing is outputting tooltip point after point, and doing 72 lines of code to cut this right here is a lot, right? It's pretty ridiculous. So I'm going to go into curve 5-axis here, and I'm going to say maximum step. Let's go 6 inches and see what that gets us. We're always going to have at least 2 vectors for the entry. So 1 vector for the entry start point, 1 more vector for the start of the cut. But now you notice we get a point here, we get a point here, and we get our exit point here. Unfortunately, there's really no way to filter out the extra entry and exit points here in the toolpath. If we're using entry exit, so if I go into entry exit here, if we're using entry exit, we get 2 extra vectors, end of story. But I don't have to use entry exit. Okay, I'm going to post this out just so you can see it. Oh, and I think, sorry about that. I think my other code expert was blocking your view that whole time, so sorry about that. But I've changed, oh, let me see. Let me move that over here. There. Okay. So I've changed this toolpath, and it only has these 4 vectors. It has the entry vectors, so this is all entry feeding down. But then I get the start vector here for my entry, I get my next vector here, I get my next vector here, and I get my exit. So really, I mean, very simple toolpath. However, if I want to get it even more simple, I can do this. Okay, if I want to make it even more simple, I can turn off my entry exit. I can go to the geometry itself. And I can extend out my geometry. So I'm going to extend it by, there we go. I'm going to extend it by 0.6 in front and 0.4 at the end. I've turned off lead in and lead out. I make sure, that my maximum step is at least the length of that line. How can I make sure that the maximum step here is greater than the length of the line that I'm driving? Well, one thing I can do is I can right click in here and I can choose the length of an entity, and then I can go pick that line itself. It tells me it's 5.228. Great. I'm going to make this 6 inches, select OK, and regenerate. And what I get here if I back plot is I get an entry vector, it drops down, I get a line that cuts, and I get my retract. If I were to, under linking, if I set this, turn off retract, and I set my feed plane to 0 incremental, I can really get this down to the very bare minimum. I've got my position vector to start, I've got my entry into the cut, or the start of the cut, I've got a line that cuts down, and I've got a retract vector, 4 moves to cut that line. Okay, rather than 70 moves if I use the default values in the toolpath. So just to show it, this one toolpath. Okay, and there she be. So we've got, our move to plunge to the start of the path. We've got our move that cuts the entire wall off, and we've got our retract, right? So we've got these kind of 4 vectors that cut that wall away. All right, we're going on to like 2.5 hours now. So thank you all for being with me. I appreciate it. I appreciate the fact that you're willing to take some time out on a Saturday to learn something new. And let's just finish this off by finishing this cut over here. So I'm going to do another curve 5-axis toolpath. So we'll do curve. I'm going to grab my 3/8 flat end mill. Second wall. I'm going to go in and edit this tool. So I know you can't see this, but I'm just editing it real quick to change the RPM and the feed. Looks like we're getting a question, will the video be recorded? I hope so. I don't honestly know because this live YouTube broadcast's a little new to me. Can you save this stream? I hope so. I mean, this is under the live. I didn't see anything specifically that said, saved or not saved under the YouTube. Place, analytics, streams healthy. Anyway, I hope so. If not, we'll try to do another one of these again. I know there is some record, so not that you probably care about the details, but in order to broadcast my screen on YouTube, I've got to run this third-party software and manage it kind of in the background, choosing what I'm displaying and not displaying. And there is recording software that's built into it's like OBS. It's Open Broadcast System, but I didn't enable the recording, so unfortunately, at least in this software, I'm not recording it. Hopefully, YouTube Live will actually record it in the background and put it up there, but I'll find out. And if not, like I said, I'll probably do this again at some point. So, let's see. Oh yeah, no worries at all, man. Okay, so I'm entering my toolpath data here. Is that my toolpath? That's my toolpath. Let's get the toolpath in place. There we go. So under cut pattern, 3D curve, I'm going to do partial. I'm going to go the other way so that we can use left this time, just to show you. Again, remember that even though I chose my tool, I didn't reset my radial offset. I think it's going to warn me when I go to select OK, but I'm not going to chance it. We're just going to fix it. So let me do my 3/8 flat end mill. I'm going to choose the curve. Partial chaining. Go that way. We're going to go on the left side and then 0.1875. And under the tool axis control, we've got tool axis control lines. I'm going to select this one line because really that's the orientation I want my tool to take for the entire path. Under linking, I am going to use entry exit just because I didn't already modify the lines themselves. And you don't necessarily always, having a few extra lines of code, I think, is a better solution for having the flexibility of being able to change these values. You enter toolpath parameters, you generate the toolpath, you see how it looks, you make changes to make it as efficient as possible. And if we backplot this, still a super efficient toolpath, right? We've got 1, 2, 3, 4, 5 vector lines. I could get that down to 3. Or actually, I'm not including the very start. So really it's 1, 2, 3, 4, 5, 6, 7. So 7 moves to cut that edge, and if I post-process this, there we go. I say yes, and here's our first cut right here. But then you notice something that happens. I've entered and exited the cut, and then all you see is this rotation. So this rotates from my first cut here to my second cut, and then I've got, some other approach move where the tool moves to the next position. So I have to be aware of getting my tool into and out of the cut. So basically from this cut, I have to safely be able to transition to my next cut. That is not going to happen if my tool ends down here. So one of the things I'm going to do, we're about to wrap up, but I'll put this in real quick. I'm going to go down into my reference points here. And on the retract, I'm going to go and I'm going to select a retraction point. So there's where my tool's retracting out. So I'm going to go create a point at Z 6 inches. And we're going to go to wireframe, point by position, and I'll put my retract point, say, here. So it's up above the part. I'm actually going to go a little higher. So let's analyze that, and let's go 8 inches. Oh, you know what? Sorry, everybody. I'm in the front plane. So I'm going to go planes, up top. Let's go 8 inches, and let's create a point right there. That's better. So now what I'm going to do in my first curve 5-axis toolpath here, hold on, let me there it is. So I'm going to go up to my retract point, and I'm going to go to the select button here, and I'm going to grab it. And you'll see that it's also relative to the plane that I've got selected down here. So really the 8 inches, the 8-inch Z position is the critical part. So I can turn off the X and the Y, and if I regenerate, what you're going to see is I make this cut down here, I retract out along the tool axis, but then I pop up over here. So if we backplot that, what's going to happen is I cut along, I pull out, but then I drop up, I jump up here, and then I move over from that position to the start of my next cut. So it's a much safer way of controlling the transition between those two cuts. All right, everybody. You know, I could I could go on forever with this. Oh, nice, former e-apprentice student here. So thanks, guys. Thanks for joining us. You know, there's always, you know, more fun stuff to cover. So I will check and see if this was able to be recorded, and hopefully it'll be up on my channel. There's more stuff coming on my channel, guys. So I can't encourage you enough to you know, to go on YouTube, subscribe. There's a lot of really good Mastercam content up there already, and there's going to be more forthcoming as I keep adding more stuff up on my channel. I don't know if this link takes you kind of directly to my channel or not. If not, search for MP101. So let me just type this into the chat. I'm just typing in some stuff, guys, real quick. So, yeah, MP101 is my basic milling class, basic post-processor milling class. MP201 is my 4-axis MT lathe post class, and then MP301 is my 5-axis post class. I'm still uploading a bunch of videos, so MP101, the basic post class, is complete. So there's 28 videos up there for that one. I'm still working on the 4-axis lathe post class, and I'm uploading all the 5-axis post class videos are produced. So I'm just in the process of uploading those. You know, probably a couple more weekends before I get them all up there. But it's a bunch of stuff coming. I'm glad, you know, everybody's able to come and hang out with me on you know, on a Saturday. That's pretty awesome. So you know, I think at one point we had a total of like 18 people watching, which is sweet. You know, hats off to you guys for, you know, taking the time to jump on and try and learn something new about Mastercam. And I'll definitely look at doing this again in the future. I think it's a great way to output content. By the way, a little bit about me. I know it's at the end, and I know some of the people have dropped off a little bit. I'm a senior applications engineer at a company called Methods Machine Tool, and we are the importers and distributors for several different lines of Japanese machine tools. So our highest end is Yazda. If you've never heard of Yazda, they're not the largest machine tool builder from Japan. They're just the best. And I say that with with all humility, but they make the world's, or at least Japan's, most accurate machine tools, and they are definitely in the running for the world's most accurate machine tools. Besides that, we also represent OKK, which is a new line for us, but they make some very heavy-duty, rugged equipment, especially if you're doing titanium or any of the HSRA materials. I would definitely give OKK a look. We have our own Methods brand, which is actually made by Litz for us out of Taiwan, but we work really closely with them to make sure that the machines are coming out to meet our specs, which are we build machines basically to higher specifications for our commodity style machines than almost anybody on the market. So it's a machine that'll compete price wise with Haas for sure, but we blow them out of the water in terms of things like we build all our machines have chilled ball screws. They're all temperature compensated. Fanuc 31i controls for the 5-axis. For our 3 and 4-axis machines, we've got the OI-MF control, but really built to our specifications. So we also represent Nakamura Tome in the United States, so high-end mill-turn machines, multi-axis lathes, and we do a ton of automation work as well. So we're a certified Fanuc integrator, and we do probably 40 to 100 serious turnkey projects every year where a customer comes to us with a complex manufacturing problem, and we develop the machine solution, the tool paths, the tools, and all the automation to feed parts in and out of the machine. So, give us a call. Oh, RoboDrill, that's the other one. That's, our number one sales machine every year, but we sell a ton of them. And they're great machines. They're only 30 taper, but the amount of productivity you can get out of one is absolutely fabulous. I see a comment from John. Yazda is the most accurate. Yes, absolutely. I don't know if you've seen it, John, but we actually have a YMC series, the Micro Center, both the 450 and the 650, and these are the highest precision machines I've ever used. So in metric mode, it's 5 decimal places for X, Y, and Z, and 5 decimal places on the rotary. So we try to measure the arc second error, and basically we're at less than 1 arc second. So our measuring equipment is some of the highest laser calibrated Renishaw systems, and we have difficulty detecting the error on both the B and the C axis. So for doing 5-axis work, it's absolutely just incredible. Yeah, and so John's mentioning a turbine blade that we did where we cut the turbine, and that was on a PX30, which itself is a super accurate machine. We cut the surface of the blade, and then we engraved a micron symbol into the surface of the blade that was 1 micron deep, which is, you can see it visually, but you can't feel it. And that's kind of the cool thing, is that down at that level, 1 micron is 40 millionths of an inch. It's half a bacteria wide. So to put it in perspective, and that's on our what we think of as the Yazda production machine. I mean, the PX30's got 33 pallets, and it's just super nice for making high accuracy production parts. The Micro Center line takes it one step further. So the resolution on the PX30 is 1/10 of a micron. The resolution on the Micro Centers is 1/100th of a micron. It's mind-blowing how accurate that machine is. Now, the one drawback for the Micro Center, it's definitely designed to make small parts to very high accuracies. So you've got an E32 HSK spindle on it, 40,000 RPM, but the E32, it's only 32 millimeters in diameter, right? So you're talking about 1.25 inch diameter tool holder. You know, the ideal size tool for the Micro Center is probably 6 to 10 millimeters for roughing, and then I've used tools on that thing that are 0.01. The smallest tool I used was 0.02 millimeters in diameter, and it had a 0.02 millimeter corner rad for doing some mold work. That basically I was taking a 1/4 inch pin, 6 millimeter pin, and I was machining an entire mold on the tip of that pin, which was pretty mind blowing. So yeah, if you guys are in the market for high-end Japanese machine tools, by all means, love to talk shop with you and see if we can help you and your company, find the right solution. Just real quick, because I would be remiss if I didn't do it. Let me do one more window here. Browser. No, that's not what I want. I don't want that at all. We don't want that. What we want is a window capture. Sorry guys, just trying to very last thing here. Window capture. Boom. Okay. All right. So let me make sure the live stream. There we go. So methodsmachine.com. If you want to reach me or anyone in the company for whatever reason, you want to check out the stuff we've got. So we've got our own Methods Machine brand. We represent Nakamura Tome, Fanuc for both robot automation and the Robo Drill line. Yazda, obviously, the highest accuracy machine tools you can pretty much buy in America. Some German companies give us a little bit of a run for the money, but I'll take that Pepsi challenge any day. To be honest, I've never seen a machine tool quite at the level that Yazda's at. OKK, believe it or not, is a close second to Yazda. They're not necessarily to the level of accuracy, but as far as performance goes, and especially in the 5-axis, super beefy, rugged, capable 5-axis machines. Kiwa makes great 3 and 4-axis equipment. You can, of course, put a trunnion table on any of our machines. We do sell vision gauge for like optical comparators and CMM equipment, and then Ocean Technologies is our EDM line for both wire EDMs and hole popper EDMs. I actually just started working on a 5-axis post for our hole popper, where we're actually doing some pretty trick things to make it mill with the hole popper, so we can do some test cuts to determine what the wear rate on the electrode is, and then we continually feed down the W axis as we're moving in X, Y, and Z in order to keep the tip of the tool at the same plane while we're milling out with an EDM, which is some pretty cool stuff. So yeah, if I can, help your company succeed, I'd, love to talk shop and see if we can, introduce you to one of our sales guys and find equipment for you that's going to help make you successful. So, thanks for hanging out, everybody. Appreciate all your time, and I'm going to go ahead and end the stream here. So, I don't know about you, but I'm getting hungry, and I'm sure my wife is missing my company. So, all right, I'm going to go ahead and close some of this stuff out here. And I'm going to go ahead and end the stream. All right, I'm going to wish you guys a great night, and I'll see you guys later. Thanks a lot.